Alright, my name is Zach Mwaldi, and I'm here to teach you about substitution, more specifically, Sn2 substitution. So, as the name implies in English, we're pretty much gonna substitute one thing with another thing. So, if we have, let's say, BR, right, we're gonna substitute it with, and then plus, let's say, NC, right? We're just switching these two. This is what the reaction is all about. We're just substituting the halide with a nucleophile. So, to draw it more generally, we have an alkyl halide, like this one, plus a nucleophile. So like this one right here. Preferably if it's, nucleophiles, I can probably teach this later, but nucleophiles are best when they have lone pairs and they're negative. What's gonna happen is that the nucleophile is gonna do a backside attack onto the alkyl halide, or the carbon that's attached with a halide atom. Halides, just as a refresher, are fluorine, chlorine, bromine, and iodine. So let's draw this more in like 3D fashion, so we can see what's going on like an atomic scale, if that makes sense. Okay, so what happens is that the nucleophile will attack the carbon atom and then kick out the bromine. And when it does that, the hydrogens, or whatever it's attached onto it, so it could be like another carbon, it will pop back, like, I'd say like an umbrella, right? Because you're kind of doing this motion where it's just popping back and it goes like that. That makes sense. So it does a backside attack where it hits the back and then hits the carbon atom and kicks off the halide, and then we get like a popped umbrella shape. So what this does is that if this shape is not chiral, but if this shape, let's say if it was R and it was chiral, most of the time, not every time, it switches to an S. What happens here, I'll show you with an example. So let's say we have this molecule, right? So what would happen is that, let's say we have this reaction right here. We have NaCN, right, with acetone. So what's going to happen is that we get that same molecule, we substitute the Br and the Cn, so the Cn, or the cyanide, it's going to hit the carbon, does a backside attack, kick off the bromine. However, it's going to switch it from a wedge to dash. So this is right now, so this is right now an R, right? Right here, we'll switch to an S. What's gonna happen is that every time it's gonna switch it from a wedge to a dash. However, not every time it'll switch it from an R to an S. There are some times where it just doesn't do that, just by the way that we do R's and S's. However, it's just the wedge will always switch into a dash. Anyways, let's talk about who can do Sn2 reactions. Okay, so right now we have a carbon to the 0th degree, meaning that there are no other carbons attached to that carbon. We have a carbon first degree, which is attached to one carbon. Second degree, 2 carbons. Third degree, 3 carbons, right? So if we do a backside attack, we do an Sn2 or put in Sn2 conditions. This one will do an Sn2. This one will do an Sn2, but a little bit slower. This one will do Sn2, however, it'll do it in the slowest rate between these three. But this one will almost never do an Sn2. It will do it at such a slow rate that's just impossibly long to do, if that makes sense. This is because right here, the carbons, they're also attached to other stuff, right? And when it's attached to this many stuff, it's very bulky for the nucleophile, right, to go here and just hit it right here. So the bulk around the central carbon prevents the nucleophile from attacking. In other words, the sterics of the third degree carbon will not allow it to do a backside attack on the molecule. Also, another important condition is that all of these, or all of the molecules we want to do an Sn2 reactions on, has to be an sp3 hybridized. This means that you can do a reaction on, let's say, you can do an Sn2 with this molecule because this carbon right here, that's the one that's attached to the halide, it's sp1, p2, p3 hybridized. sp3 right here. However, if you got, let's say, this molecule, it will not perform an Sn2 reaction. Reasoning is that it's sp1, p2, sp2 hybridized, and you cannot perform Sn2 reactions on an sp2 hybridized carbon. What you also need to know is that Sn2 Sn2's rate at which the reaction is conducted Okay, so the rate at which an Sn2 reaction happens is directly correlated to the nucleophile and the alkyl halide. This means that in the reaction, if we double the amount of our nucleophile, so let's say we have Na N3, right? That's the N3 is our nucleophile. If we double that, that means our rate will double. Or if we have, let's say, this molecule right here, if we double this molecule in this reaction, if we're doing sodium azide and this molecule, and we're trying to do a backside attack with an Sn2, if we double the amount of this molecule in the reaction, the rate will double. This means that the whole mechanism is one step. So when you do an Sn2, this means that the nucleophile hitting the central carbon and then kicking off the iodine is happening in one instantaneous step. And there are no multiple steps, if that makes sense. Another thing that we need to consider is the need for a polar aprotic solvents, right? What does a polar aprotic solvent mean? It means that it's a solvent that doesn't have an acidic hydrogen. That's the technical term. The more easier term to understand is that it's a solvent that has one end that's negative and no strongly positive end, if that makes sense. It's polar, it has a positive and negative end. However, the positive end is not that strong. The negative one trumps it. If you don't understand what I'm saying, the most popular polar aprotic solvents that are usually on exams are this one, which you use for your nail polish, acetone. We also have acetone, but with the carbon switched out with the sulfur, or we have DMSO. We also have acetonitrile, and the two less popular solvents, but they're still polar and aprotic. We have THF, and finally we have DMF. These are the solvents that you're gonna see in your questions. Why do we need a polar aprotic solvent? Reason is that, let's say we have this example. So we have this molecule, right? So example 1, and we want to do a backside substitution attack, or backside attack, or an Sn2 on it to switch it out with, let's say, azide, this nucleophile. So we want to switch these out, right? There, like in real life, we don't have just azide negative ions to, like, put in solution. We need it as a salt. So what we do is that here, we put this through sodium azide, right? And then we put it in a polar aprotic solvent with this, with our reactant. So we put it, let's say, acetone. So what will the acetone do is that sodium azide, it's Na plus and N3 minus. They're together in a salt form. And the acetone, what will do is, that it will solivate the sodium and the sodium azide. You see how this side is negative because it has lone pairs, and this side is slightly positive, but it's not very positive. Slightly. It's not as negative, or the strength of charge is not as strong as the negative charge on the oxygen. It's just slightly positive. So what we'll do is that it will strongly attach on the sodium and solivate the sodium. However, the azide is more free to move in solution. It's slightly solivated, but not as much as the sodium. So what will it do is that it will leave the azide ion free to flow around. It will be a lot more freely removed and do a backside attack on the iodine and pop it off, and you get this as our final product. Thank you guys for watching, and I'll probably leave some practice problems down in the description with answers. And yeah, you guys have a great day.